So this video is going to be on color and specifically light color, not paint, light. So light color is very, 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 very different from paint color. If you take paints and you mix all the paints together you mix your red and your green and your purple and you just mix everything together, you kind of get like a poo brown and it's not very attractive. Light doesn't work that way. Light, when you mix it all together, you get white light, or the reverse of that. If you take white light and you separate it all out, you get all the colors of the rainbow. So light is like virtually the opposite of paint. And really, for this lecture to make sense, you can't think of this in terms of your paintbrushes. This won't work. You have to give that up completely and just look at it with new eyes. We can take all the colors and mix them together and we'll get white light, just the opposite of your paints. All right, so different wavelengths are your different colors. So your red's about 700 nanometers or so. Your blue for about 420, it looks like there. But each different wavelength is a different color. And so you can see you have like a red photon, which would be one wavelength, and a yellow photon, which would be another wavelength, and a green one, which would be another, and a blue one, which would be another. I want you to notice here that the yellow is actually between the red and the green on the spectrum, and that'll be important on the way our eyes perceive color in a minute here. And since we're humans, what we really, really care about is our perception. Okay, talking about our perception of light, it is obviously a spectrum that goes from left to right. It is linear. You have certain wavelength and a certain frequency on the left side and another wavelength and frequency on the right side, and it doesn't loop back around, but you will always see a color wheel. In art class, even when you look at fashion, they'll talk about this color wheel, and you think, well, that's weird because, it's linear. But the way the color wheel works, which is kind of interesting, is you put your primary colors on it. Your primary colors for light are red, green, and blue. And their complementary colors are on the other side of the wheel. And what a complementary color is in light are the spectrum that's missing the red. So if you have red on one side of the wheel, the opposite side of the wheel would be the colors that are missing red. If you have green on one side of the wheel, directly opposite are the colors that are missing green. There's no green in them, right? So they're called complementary colors. All right, when we look at additive colors, we need to look at primary colors, and then we're going to look at secondary colors, and then we'll talk a little bit about how they reflect off and how we see them. So your primary light colors are red, green, and blue. And we can make all the other colors with red, green, and blue. And I know you're still thinking, but green is, blue and yellow mixed together. No. That's paint. We are doing light here. The primary colors are red, green, and blue, and we will make the other colors out of this spectrum. Okay, so as we start mixing red, green, and blue, if those are the primary colors, and they are, when you mix them together, you get white light back out. So if you take a look at this projector here, you have red, blue, green. Those are the primary colors, and you have in the middle white light, which is correct. Then you have the secondary colors, which are a blending of the two primary colors. So you blend red and blue, and you get magenta. You blend red and green, and holy crap, you get yellow. Yes, yellow when you blend red and green. Remember, I said at the beginning of the presentation that yellow sits between red and green. So when we blend those, we perceive yellow. All right, and then between blue and green, you get a color called cyan, which fortunately for you looks kind of like blue-green. Also because there's nothing between blue and green, which is why it doesn't blend to some new color. All right, so here we go. Here's what I just said, but written down for you. When you take red and blue, you're going to get magenta. And I know, again, you're thinking, well, that makes sense because it's purple. No, no, no. This is light. Don't even think of it in those terms. Red and blue gives you magenta. Red and green average out to yellow. Go look on a rainbow. It's in between them. Red and green, yellow's in between them. Your brain averages that out to yellow. Blue and green is cyan, and cyan is a bluish green color. All right. Yeah, I'm going to repeat this, but it's okay. So you can have a yellow wavelength, a yellow frequency that hits your eyeball. And you know what you see? Yellow. You can also have red and green hit your eyeball, and you know what you see? Yellow. Your brain takes those and averages them, and it sees yellow, the in-between color. Okay, so now we can start kind of subtracting out some color. This is just kind of for fun. You can make shadows and block light. So we have, again, our primary colors here, red, green, and blue light shining down, and in the center you get white. Here's the center. Then they put a golf ball just for fun and blocked some light. So you go, okay, here's I think it's supposed to be a cyan shadow. If it's a cyan shadow, what is missing of the red, green, and blue? Red is missing, so you've blocked the red light there, and what you have is green and blue. This is going to be a magenta shadow, all right? And what is blocked to make magenta must be green, because magenta is red and blue mixed together. All right, over here we have a yellow shadow, so we know that that would be red and green mixed together. So we must have blocked the blue light. Okay, those are just shadows with some of them blocked out. All right, mixing colors. So there's different ways to mix this up. If you take magenta plus green, you get white light. And you think, well, why is that? Well, let's think about it. Magenta is red plus blue. And when you add the three primary colors together, red, blue, and green, you get white. So you have red and blue in your magenta, you add it to green, and bam, you're back to white. Or you can do yellow plus blue, right? Yellow plus blue is going to be white light. Again, why? Because you have red and green, which is your yellow, and then you add in blue, your third primary color, and you get white light. Obviously, the one that's missing here that you don't have to write down is you could take cyan and red, and you would also get white light, all right? Okay, so on a color monitor, you can actually do that, and they do that. You only need the three primary colors. You need red, green, and blue. And you can actually create the other colors using those emitters. And the way you would do that if you wanted to create yellow is you would just have it be red and green, and your eye would see yellow. So imagine inside of your eyeball you have these three different kinds of receptors, and that's true when we look at color receptors, all right? Not for black and white, but this is true for color. There are three different kinds in your eyes. There's one that is receptive and gets excited and triggers your nervous system when blue light hits it. And we're going to imagine this to be Mo. And yes, I know you don't know who the Three Stooges are because this is really, really old, but you know, that's just life. So imagine in your eyeball, you have, Larry, Curly, and Mo in your eyeball. And Mo gets excited when blue light hits him. Curly gets excited when a green light or photon hits him. And Larry gets excited by the red, all right? These are receptors inside your eye. So what would excite Mo? Mo would be excited either by cyan or blue would excite Mo. Curly could get excited by anything with green light in it. So green, again, cyan or yellow. And then Larry would get excited by the yellow, which has the red, or the red. All right, now to see yellow, we need to excite two of these knuckleheads, right? To see yellow, we want to excite Curly and Larry, and then we will perceive that as yellow. To do that, you can either use a actual yellow photon, which is, a certain wavelength, but you can also do red and green, and that will excite Curly and Larry in your eye, and you will see yellow. All right, for you to see magenta then, we would need to excite Mo and Larry. And when both of those get excited in your eyeball, those receptors get excited and trigger your nerve, you see magenta. Again, you can do that with the blue and the red, and there's actually no kind of pure magenta light that works. So for that, you're going to get blue and red to see the magenta. Okay? Seeing white, we mix all three of those together. Or we can mix, the complementary secondary color with the primary color, which is the same thing as mixing all three of them together. Okay? Color blindness. Well, if you're colorblind, you're missing one of these guys. All right? And so you're missing one of them, and the other ones try to compensate for that, but you're not really getting the real colors. So this is the color blind test. If you look at those two circles, you should see a number inside of them. And if you don't see a number written inside of them, you are probably colorblind. Which, is a sex-linked trait, but that's genetics. We won't go into that. All right, after image. What we're going to do is we are going to stare at something and fatigue the receptors. So you're going to stare at something and fatigue that receptor to the point where it just doesn't want to deal anymore. And when you've done that, you should see the complementary color. Think color wheel here. All right, so if you stare at the red, stare right at the center of the red cross and don't move your eyes for fully 10 seconds, which we can see if I can talk for a full 10 seconds. I have a timer going. Keep staring, don't look away, keep staring right in the center of the cross, keep staring, 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 staring. We're fatiguing your red, which should leave you cyan, I hope. If you keep staring and you're looking there, you should see cyan. You fatigued that red sensor to the point where it was just, okay, I'm seeing cyan crosses now. But you fatigued your red sensor, so you should see cyan. Oh yeah, this is fun. So again, you got to stare at the middle. Stare, 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 stare at the middle. Don't look away. Choose one spot. Don't let your eyes wander around. You got to do it for a full 10 seconds again. And I will just keep blabbing on for 10 seconds so that you get a good after image. While I'm blabbing on, you should start contemplating in your head which secondary complementary color you should see when I switch the side. When we remove the red, which we're fatiguing just on one spot of your eye, what should you see? We already did that one. You should know that one. Okay, white light, if we take out the green, we're just left with red and blue. What should you see there? And if we take out the blue and we're just left with red and green, it sounds crazy, but you know what you should see there. Don't move your eyes. Yeah, did that work? Because it certainly worked for me. I'm seeing those colors. Okay. So your additive color wheel is just what we just went over. That's why the color wheel works. That's why you have those secondary colors. Opposite of red is cyan, just like you just saw. Opposite of blue, yellow. opposite of green, magenta. All right, so color vision in the eye. You got your 3 types of your cones, which we just fatigued and had a little fun with. And then you have what's called a rod, and that just does the black and white. That is how dark something looks. Even if there's color with it, your rods will still get stimulated. Okay? And the eye is not a perfect optical instrument. And the color wheel is a distorted cone shape. And the reason is it would be perfect if we had, 33% of each of the receptors. We would be right in that white light. But we tend to not get exactly 33%, 33%, 33%. So you will have distorted, more to the greens or oranges, or whichever way, whichever way you are missing some receptors. Okay, so why do we see colors when you look at a red ball? Well, what's happening is you have white light hit the ball, should be white light, and all the colors are absorbed except for red. And red gets reflected into your eyeball, and you see red. So that's, look at anything. Look at a yellow banana. Why do you see it's yellow? Everything else is absorbed. Yellow's reflected into your eyeball. Okay, so name that color. Well, if you had all blue, green, and red, you can guess what quote-unquote color that would be. Or if you just had red light, what color would that be? Red. And yeah, dark brown, burnt sienna. Ugh. Okay, same thing. Name the color. Blue, blue-green, green mixed with red, and blue and red mixed together. Okay, subtractive color. Now these aren't lights that we're shining. These are going to absorb the light and only allow through certain colors. That's different than we're shining a yellow light. This is a filter that's going to take everything but yellow out, which means on the other side you could have red and green. On the other side of the cyan filter you could have blue and green, and on the other side of the magenta. So when you overlap them all, you have taken out all of the colors possible. Okay, so let's look at this. This is just when you have a soap bubble. Did you ever wonder why? And we're actually going to do a little more on this in reflection and refraction, but do you ever think of why you can see colors in something that is just white and there's white light hitting it, or it's clear and there's white light hitting it? Well, it depends on the film's thickness, and there's actually some interference going on. And so when you remove red, you remember what you see if you take out red? You see the cyans, right? Or if you remove the blue, what happens? And so what's happening is the reason you see some colors is either the reds, the blues, the greens, whichever colors are getting removed by interference, hitting this very thin film. All right, so you ever look at your printer? Printing ink is so expensive. You have, I think it says on it MYCB, but it is magenta, yellow, cyan, and black. And you buy your colors. Well, what it does is it mixes together and you can form literally every single color using that. And what's kind of fun here is if you look off to the left one, that's without the black and white, right? And then you add in the black filter and you get all the depth and you can really see what's going on. All right, so check yourself which inks are mixed for the bright red balloon and the dark red dress.